Okay, so this video is going to be on Unit 6C, that handout. Um, and it's going to be more stuff related to similar polygons. So if two polygons are similar, remember one's kind of like a big version usually and one's a smaller version, and they look the same. It's like you just shrunk one down. So they have the same shapes, but the sizes might not be the same, right? So not necessarily the same sizes. If they were the same size and the same shape, then I suppose you could still call them similar, but if they're both same size, same shape, you'd probably want to call them congruent instead, because that tells you more info. And then if two polygons are similar, so here I'll draw an example. Like let's say this one is similar to that one. So let's say you know that those two are similar. Then the corresponding angles are already congruent. This one goes with that one. They're exactly the same. This one goes with that one. They're exactly the same. This one goes with that one, and so on. And this one goes with that one. The sides aren't identical. They're not congruent. But you can set up these proportions like this side over that side equals this side over that side. So you're allowed to set up proportions instead of saying the sides are exactly the same. So if you remember CPCTC, that goes back to last semester. CPCTC represents corresponding parts of congruent triangles are congruent. And if you remember how it shows up in a proof, what happens is you start out with various things and you're trying to match up sides and angles up here in order to get something like SSS or SAS or ASA, and then there are a couple other ones. And the goal is to get, once you get that, you have a triangle congruent to a triangle. So up above, you're trying to match up a pair of sides, pairs of angles, stuff like that to get SSS or SAS. Then after you have that, after you have congruent triangles, you can use CPCTC to match up any other parts of the two triangles that you haven't already matched up. So like you might either have angle congruent to angle or side congruent to side for a CPCTC step. Okay, now there's going to be something like that for similar triangles. So, but we can't do it all in one abbreviation. So what I did was I split it into two. The A is for angles and the S is for sides. And remember, the angles in similar triangles, since they're similar, the angles are congruent, right? So this is going to be corresponding angles of similar triangles are congruent, because the corresponding angles are exactly the same. This one down here, corresponding sides of similar triangles are, and then the P is the corresponding sides are in proportion. Okay, and then we'll figure out how to use those when we start doing some proofs. Okay, so I'm actually going to skip number one for now. We might come back to that on another day, but I'm not too worried about doing one right now. So I'm going to skip that. So let's look at two. So in this one, you're already told that the pairs of shapes are similar to each other. And so then we have to find missing angles. So in the first one, and you know that if you have similar polygons, that the corresponding angles between them have to be exactly the same, right? Up here, if you have similar polygons, corresponding angles are congruent, so they're exactly the same. So in this one, you can kind of guess, well, if this one's 30, this angle right here probably goes with G over there, so this one's got to be 30. The 105 is the obtuse angle. This is the only obtuse one in the picture, so that one's got to be 105. And then to get the remaining angles, well, it's 180 degrees in a triangle, and if you subtract the 105 and the 30 put together, you'll get, I think it's 45. Let me check. Yeah, it's 45. So 45 degrees here, 45 degrees there. Okay. In the second one, Let's see. This one looks like it's got to go with the 100 to me. The 65 down here looks like it's going to go with Q over here. The 60 over here looks like it's got to go with S over there. And then to get R, well, it's a quadrilateral, so four sides has a total of 360 degrees. So then if I subtract out the 100, the 60, and the 65, we're left with 135 degrees for N and R. Okay. So in the next one over here, let's see, we got two 90s already matched up. This angle in between the two 90s is going to have to go with that angle over there, so we'll figure that out in a little bit. The 110 right here looks to me like it's going to go with the P. You can kind of tell that these shapes are sort of flipped across that line down the middle, and then the one on the right is shrunk down a little bit. So P here is going to be the 110. The 95 where W is over here is going to go with that A. And so now we filled in all the angles except for E, which goes with Z. And so this one has 5 sides. So to get the total degrees, we'll do 5 minus 2 times 180, which is 540. And then we can subtract out from 540 all the angles that we do know. So minus, let's do 95 plus 90 plus another 90 plus a 110. And so then there we end up with 155 degrees. So then this angle is 155 and this angle is 155. Okay? All right. So then let's look at 3 here. So scale factor is, I don't think I've talked about it formally in class yet, but we did a homework problem where I can't quite remember the shapes off the top of my head, but it's something like, you had some weird quadrilateral and then some other similar quadrilateral that was a different size, and I think one of them over here had like a 20 and one had a 15 for the sides that match up. So this 20 and that 15 you could figure out had to go together. So if I said what's the scale factor of the big one to the little one, it would be, well, you know, you can set up 20 to 15. The scale factor is basically any ratio that you know you can set up between corresponding sides, but you simplify it first. So this one would be 4 over 3 would be the scale factor for this problem here, of the big one to the little one. So in the problem down below, we'll do the scale factor of the little one to the big one. So scale factor, and then down below I'll say of small shape compared to the big shape. And otherwise I would specify big shape to little shape or little shape to big shape, so you know which one goes first. Well, the only sides that both from this shape on the left and this shape on the right that have numbers in the same places are the 3 here and the 4 there. So you can tell that the 3 and the 4 have to go together. So it's 3 to 4, and then that can't reduce at all. So that's it. There's the scale factor, 3 to 4. Or 3 over 4 if you prefer that. Okay. So then let's use that to help finish the problem. So I'll match up these other sides. The y goes with 8. The z goes with 10. And then the left over here, this 4 on the bottom. Whoa, how did I erase all that? The 4 down here. Oh my gosh. The 4 here goes with the x there. So let's set up some ratios. So if I do the little red over the big red, that's 3 over 4, equals, I don't know, let's do the x's. So that's the little gray over the big gray, 4 over x. So then if I cross multiply, 3x equals 16. So x equals 16 over 3. If I do the y's, I'll do the little red over big red again, 3 over 4, equals little blue y over big blue 8. And you can cross multiply if you want, but you can also, if you see this trick with a proportion, to get from 4 to 8 you have to double it. So to get from 3 to y, you have to double 3. So y ends up being 6. And then we can do the same thing. Red over red equals green over green. So 3 over 4 equals z over 10. And then if I cross multiply, 30 equals 4z. So 30 over 4 equals z, which is the same thing as 15 over 2. Or if you wanted, you could say 7.5. Okay. Now, if I asked you, what if you added up all 4 sides of this and compared it to all 4 sides of that? So the ratio of the perimeters is also going to be 3 to 4. Right? It's the same thing as the scale factor over here. So that's convenient for the next problem. The next problem says STA is similar to RKY, and you know that the scale factor is 7 to 9. So here, let's say STA, so scale factor, all right, SF, of STA to RKY is going to be 7 to 9. Okay, well the perimeter of STA is 42, and I want the perimeter of RKY. So I can set up this, perimeter of RKY. I can set up this. Well, I know that the 7 is the first number, so that goes with the first triangle, and the 9 is the second number, so that goes with the second triangle. And we know that the perimeters will have the same ratio. So I'm going to set it up like this. 7 goes with 9 the same way that 42, same way that 42 goes with the perimeter of triangle RKY. So you can cross multiply and do all that if you want, or you can see, well, 7 to get to 42 I multiply by 6, so to get from 9 to that I have to multiply by 6, so 9 times 6 is going to be 54. So that's the perimeter of RKY. Okay, so that's 4. Let's take a look at 5. Okay, so in 5, I give you the first way to prove 2 triangles are similar, and I describe it. You can actually prove that 2 triangles are similar. So like, let's say here's one triangle, here's another triangle. If you can match up all 3 pairs of angles, so this, if the 2 lower left ones are equal, and the 2 top ones are equal, and the 2 right ones are equal, then you have all 3 angles of one triangle matched up with all 3 angles of the other triangle. That's enough to say the 2 triangles are similar. But you can actually get away with just 2 pairs of angles. Because if you know 2 pairs of angles are the same, then the third ones have to be the same anyway. So it turns out if you can say, well, this angle here matches that angle there, and this angle up here matches that angle up there, then the 2 triangles are similar. So that's called AA similarity. So that's kind of like up here in that proof, instead of congruent triangles, we're going to aim for triangles similar to triangle. And now one of the reasons will be because of AA similarity, and then we can use like CASTC or CSSTP as kind of the version of CPCTC that we used to do before. So we'll eventually do that, but not yet. Pretty soon though. Okay, so let's come back down here. So the goal is to match up 2 pairs of angles. Okay, so in 5A, we've got the 60s already matched up. But I don't know what the missing angles are, so let's figure out what those are. If you did 180 minus 60 minus 62, you'll end up with 58 here. And if you solve for the missing angle in this one, you'll end up with 66 there. So these triangles definitely are not similar, because we only have 1 pair of congruent angles, not 2. Okay. If you look at the second one, well, the 50s already match up. And then if I add up the angles and try and get them to equal 180, then this one has to be 70 degrees. So now I know that the 70s match up. So you don't even need to bother solving for the third one, but if you did, it'd be 60. But you already have one pair of angles here and one pair of angles there. So yes, they're similar because of AA similarity. And the next one here, we've got the 40 at the top, and it's an isosceles triangle, so we can use that isosceles triangle theorem, the one that starts with the sides and gets to the angles, to say that these two angles are the same. Well, if there's 180 degrees, I take away 40, there's 140 degrees left, so this is 70 and this is 70. Well, you could work out what's over here in this triangle, and if you did, you get 75 here and, 30 there. None of the angles are going to match up, so no, not similar. Let's see, D. We've got one right angle here, so then this one has to be a right angle too. But then I don't know anything else about the remaining angles. There's nothing that says these bottom ones have to be the same or that this has to be the same as that. So that's as far as you can go. So we only have one A, not one pair of angles, one A out of the AA. So maybe some other angles match up, but I don't know for sure, so not enough info. In the next one, we still have two triangles, but they overlap. So let me draw them separate first. So this one's 45 in the little triangle. And then in the big triangle, we got 45 here, 45 there. And then if you figured it out, the remaining angle at the top here would have to be 90. But then that's as far as you can go. You can match up the 45s, but there's nothing else that I can definitely match up. I don't know that this has to be 45, and I don't know that that has to be 90, because I don't have any other info. So this one is just not enough info again. And then in the last one, probably the easiest thing to do, or sorry, not the last one, F, probably the easiest thing to do is match up these vertical angles, because vertical angles are congruent. So then we've got the right angles matched up and the vertical angles matched up, so we've got AA similarity. And then in the last one, I've got parallel lines here. So parallel lines give you this. This angle here and this angle here, they're corresponding angles with the parallel lines. Remember, parallel lines give you corresponding angles that are congruent. So, and if I move this over, you can kind of see that a little bit better. Right? You can see that those are corresponding. So, let's see if I can get that back. Okay, so these two angles are the same. Same deal on the other side over here. These two angles are going to be the same for the same reason. So, if I draw those two triangles by themselves, there's the little one on top. Here's the big one that the little one is on top of there. So these two triangles definitely are similar because of AA similarity. And in fact, you could have gotten away with leaving off this pair of angles over here and saying instead, well, notice this angle at the top is the same for both of them. So in a proof, that would be a reflexive step if you wanted to do that. Okay? So let's move on to the next example, and this one's a proof. So in 6, we're going to prove this weird thing right there. Okay, now don't worry about that yet. Let's start out with just the given. So angle 1 is congruent to angle 2, given. Okay, and I'll mark it in the picture. And you know we're going to deal with similar triangles, so since they overlap, I'll also draw them separate. So actually, let me do black for the main drawing. So here's CAB and angle 1, and here's DEB with angle 2, and we know that 1 and 2 are already the same. So you could do a couple of things. You could say, so CA is parallel to DE now, because 1 and 2 are corresponding angles that are congruent, so they give you parallel lines. Or you could, and by the way, this step already gives me a pair of angles matched up. So that's good. All I need is one more pair of angles. And if you look at the picture, the easiest angle to match up is angle B. It's itself. right? They're the same angle. So in step 2, I can say angle B is congruent to angle B. And when something's congruent to itself, that's reflexive. So now I've got the second pair of angles matched up between the two triangles. Okay, so now I can say the triangles are similar. So if I call the first one triangle CAB, so CAB goes from no curve to one curve to two curves. Then this one's going to go no curve, one curve, two curve. That's going to be DEB. And then the symbol for similar, remember, is one squiggle. It's very common to accidentally put a congruent sign there instead of a similar sign, so be careful about that. I find that that's a very common mistake students tend to make, and I made it this morning anyway. So, all right. Now the only reason we have so far is AA similarity. Eventually we'll learn some other ones. Okay, so that's the second part of the proof. We matched up some angles, then we got AA similarity. So the part that comes after that is the CPCTC equivalent, right? It's either going to be way up here. It's either going to be corresponding sides are in proportion or corresponding angles are congruent. So let's come back down here and take a look at what we have, right? We're trying to prove stuff that deals with sides. So I'm probably going to want to choose the one that says corresponding sides, not angles, of similar triangles are in proportion. Now you don't have to write all that out. You can just write CSSTP if you want. By the way, that abbreviation, that's not a common one that you see in textbooks. I just made that up because I hate writing out the whole thing. So CPCTC, the one from last semester, that one gets used in pretty much every geometry textbook. Okay, so that's what we're using. And then the question is, well, what proportion do we set up? So I need to set up something that says something over something, one side over another side equals one side over another side. Okay, well, let's look at the sides that are in what we're trying to prove. We've got BD right here. Well, BD is this side over here. Well, BD has to go with this side right here, CB, which is the same as BC, which is this one. Okay? Let's look at another side. CA is another side that's in the proof. So here's CA. Well, that one has to go with DE. And here happens to be DE right there. So I'm going to set up a proportion using the red sides and the blue sides because that's what is going to come in handy for the final step here. So let's set up our proportion. I'll go blue over blue. So CA over DE. So the big blue over the little blue equals the big red CB over the little red DB. Now I'm going to actually switch the way that I wrote the red ones. CB is the same thing as BC. So, and the reason I'm going to write BC is because that's how it appears up here in what we're trying to prove. Same deal with DB. I'll write that as BD instead. So BC here, BD here. Okay, so I've got the right four sides taken care of now. So if you think about what you often do at this point if I give you a proportion, a common step is to cross multiply. And if we cross multiply, then we've got BD times CA, right? BD times CA equals, and then over here we got BC times DE, right? That's what we ended up with. And that's what we were going for. That's the proof right here. That's this. And the way we got it was by cross multiplying the step before it. So it's just cross multiplication. If you just write multiplication, that's fine with me. Multiplication. Okay? So then there's one last problem to do. I'm not going to do them both. I'm just going to do the first one. So let's do 7. Okay. So in 7 we got two triangles. We already have one pair of angles matched up. I'll draw the triangles separately. So So here's 4, here's y. We don't know this side. I'm going to call this side x, so we'll solve for x too. And then in the big triangle, we've got this side, which is y plus 3. 6 is on the bottom, and then this side is 4 plus 2, so that's 6. And then we already know that this angle and this angle match up. Now there's another pair of angles that match up. You could match up the top angle. That's probably the easiest one for reflexive. And then you know, okay, I've got AA, so the two triangles have to be similar. And if the two triangles are similar, then I can set up some proportions. So the most useful one's going to be the 4 goes with 6, because those are both numbers. 4 over 6. 4 goes with 6 the same way that down here, x goes with that 6. Well, if you think about it, you can cross multiply if you want, but if 4 over 6 equals x over 6, x has to be 4 here. Okay, and then the other one, the y is going to go with the y plus 3, the same way the 4 is going to go with the 6. So 4 over 6 equals y over y plus 3, and then we'll cross multiply. And if you wanted to, you can reduce that too. I just got lazy there. I didn't think about it. 4y plus 12 equals 6y. So 12 equals 2y. So y equals 6. Okay. I'm not going to worry about the last one right now. We'll get around to doing some more of these. We'll be doing a ton of these this unit anyway. All right, I hope that helps a little bit, and I'll see you guys soon.